So internal flow, my screen is shared. Okay. So previously what we discussed was flow over surfaces, right? For example, if this is a surface, there would be some fluid which might be coming like this, right? And I mean, the fluid is coming like this, and slowly and gradually it is going to form a thermal layer and a velocity boundary layer. And but this time what we are discussing here is flow inside a like internal flow basically. So it could be a circular pipe in which we are looking for the flow of the fluid. So initially it all has the same velocity. Okay, it has some velocity, which is called Vm, mean velocity. It enters and slowly and gradually because of the friction due to the surface of the walls, there is no slip condition here. Okay, so because of this no slip condition here, gradually the front initially looks like this, the velocity front, then it becomes more like this, and ultimately it becomes perfectly parabolic. Okay, now when does this happen? This happens when the flow is fully developed. So this region is called developing region, and after that is, I mean, there's no limitation, it could like go on developed flow. This is how it happens inside the uh, fluid. Now the interesting part comes when, should I keep the slide here? I think should be good. Okay, so now the interesting part comes wherein uh, we discuss about how this internal flow causes is the, okay, my internet connection is unstable again. Why is it so? Never mind. Okay, so this is how the internal flow works. There are a few correlations which are there specifically for internal flow. So I'll just write them down here because I don't have time to discuss how they are derived. So the mean velocity is 2 over r square. This is for a circular pipe, okay? Integration 0 to r v as a function of r comma x r dr. And the temperature, the mean temperature would be 2 over mean velocity r squared integration 0 to r v t r dr. Then obviously our Reynolds number is rho Vd over mu, which is rho times Bm times d over mu. What is d? D is dh here. So if it's a circle, it's the diameter itself, which is the hydraulic diameter of the system. Just in case we have different shapes, the dh can be calculated as, so now if we have a laminar case, let's say we have a, we will have the hydraulic length LH for a laminar system would be 0.05 times RE times D. And the thermal boundary layer for the laminar system is 0.05 times RE times D times Prandtl number. So this is how you can get a sense of what Prandtl number actually means or gives an hint of, because Prandtl number is basically the ratio of uh, the hydraulic length, uh, a hydraulic so this is basically the length which it takes for uh, the whole flow to become fully developed, which is called the entry length. So Prandtl number is entry length, the hydraulic entry length over the thermal entry length. This is how another way we can define the Prandtl number in terms of internal flow. Now, what if the flow becomes turbulent? In the case we have a turbulent flow, we will have L, the thermal boundary layer will be almost equal to the hydraulic boundary layer, which will be almost 10 times the diameter. So even in the simulation environments, wherein let's say if you want to simulate like if you're using ANSYS Fluent and if you want to simulate the flow of fluid inside a pipe, even if you're taking a 2D case, you will have to generally we assume that if you want to start calculating the properties such as nozzle number inside the flow, you calculate after a certain amount of length, which is 10 times the diameter. After that, it is safe because the flow has fully become developed. Before that, it's difficult. I mean, the nozzle number might be relatively very high because the flow has not yet developed. But after this, it becomes developed. Now, if there is a heat flux coming in, so from outside, if there is a heat flux, if there's a heat flux, then we will have Q dot as Q dot S times AS. So this is heat flux per unit area. Okay. So Q dot SAS is M dot CP TE minus TI. TE is temperature at the exit. Temperature at exit. And this is temperature at entry. Okay. So this is how you define how the heat flow happens in the case we have a heat flux coming in from the outside. Just in case we have a constant surface temperature for the pipe, it will be like this. So for Ts is equal to constant. So for this case, we will have Q dot is HAS delta T ln. So this is the log mean temperature difference LMTD, uh, which is m dot Cp Te minus Ti. Okay, and from this you can actually calculate Te. What will be the exit temperature? Exit temperature would be Ts, temperature of the surface, minus Ts minus Ti times e to the power minus HAS over m dot Cp. So this is how you calculate the exit temperature of the fluid. Now, what is delta T ln? Log mean temperature difference is defined as delta T exit minus delta Ti. Okay. Maybe, sir. Delta Te minus delta Ti over ln of delta Te over delta Ti. We will discuss more about this once we'll be solving the problems for today. I think I have 2 or 3 problems for today. I could not spare time this time properly for this topic, so I'll try my best to discuss the problems correctly. Just in case I make any mistakes, please let me know. I mean, I have the answers, so Like I've tried them once, so I won't give you wrong answers for sure. But just in case I make a mistake in the methodology which I'm using to solve the problems, you can let me know. So okay, I think that's all for the theory. There are a few correlations which come for the, like if there's a rough surface, what is going to be the friction factor, and apart from that, also some correlations for the Nussel number. But all those are there in the data book which I've shared with you guys. So if you just refer to it, it's going to be okay. All right. Yep, I think let's jump to the problems directly. Okay. So this is the first problem. So air at pressure of 1 atm enters a thin walled with a diameter of 5 mm, long tube which is 2 meters long. So very thin tube, 5 mm diameter and 2 meters long, the inlet temperature of 100 degrees Celsius, and a constant heat flux is applied to the air from the tube surfaces. Okay, so we have a tube. I'll make it thicker because I want to solve the problem. It's easier to annotate if the figure is bigger. Okay. So this length is 2 meters, and this is, how much is this? 0.005 meters. And air is entering like this. At the inlet temperature of Ti, okay, Ti is 100 degrees Celsius, and m dot is 135 times 10 to the power minus 6 kgs per second. This might look very less, but air, because air is very less dense, that is why even the mass flow is very low, still the velocity might be decently high. Now it says if the tube surface temperature at the exit is 160 degrees Celsius. If the tube surface temperature at the exit is 160 degrees Celsius, determine the heat rate entering the tube. Okay, so at this point, Ts out is 160 degrees Celsius. Uh, Determine the heat rate entering the tube. So how much heat rate, what is Q dot here? This is what they want us to calculate in this problem. Now, Q dot is what? Okay. And they want us to evaluate all properties at T equal to 400 Kelvin. This is very important for internal flow, especially because you have to calculate every property at the mean temperature. So if you usually they would give you a specific temperature, and you use that temperature to calculate the properties of air or whatever fluid you have got. Just in case they do not provide, there is a separate way to calculate how is the mean temperature, how do we calculate the mean temperature and the average temperature inside the tube, and based on that you calculate the properties. I might, in the current set, I don't think I have a problem which discusses that, but just in case it pops up, I'll discuss that. Okay, so I can jump back to the black pen. And yep, you can take, I think, 1 minute to think over, ponder over the problem. Meanwhile, I'll open my solution and then I'll discuss. Okay, let's begin. So they're saying that T mean has to be taken at 400 degrees Celsius and P is 180. At these things, we have properties of air. So properties of air as mu is 230.1 times 10 to the power minus 7 Newton second per meter square. Prandtl number is 0.69 as usual. K is the thermal conductivity 0.0338 is also typical thermal conductivity of air. And then we have Cp as 1014, I think. Yes, 1014 joule per kg Kelvin. Either these properties will be given to you or you'll have to look up in the textbook. So how do you begin the internal flow problems? First of all, you determine whether the problem is laminar or turbulent, and then you next begin with whatever final state they have given. Till that time, has the situation become like fully developed or not yet? Depending on that, we will see how to approach the problem. So first of all, let's calculate the Reynolds number. So Re is rho Vd by mu, which is uh, so for a circular pipe, it is 4 times m dot over pi d mu. How you just calculate, I leave it up to you. Okay. Re is rho Vd over mu. Rho times V times dH over mu. How does this bring up to this? You will have to think. I mean, simple. Density is area, then density times area times length is volume, and then that's how you bring up m dot, and a few things cancel out. You'll reach this expression. Okay. So this is 4 times m dot. We have been given m dot, right? 135 times 10 to the power minus 6 over pi times 0.005 times what is mu? Mu is 230.1 times 10 to the power minus 7. If you calculate, RE will come out to be 1495, around that. Actually, 1494 to be very, very specific. Okay. So this is our RE. Now, is this laminar or is this turbulent? Okay, I forgot to mention inside the internal flow, especially inside the pipe flow, if RE is less than 2300, it is laminar. So our laminar equations will be valid. So because we have a laminar flow, so with the laminar flow, uh, the hydrodynamic entrance length and the thermal entrance length would be x for, so x hydraulic is 0.05 times d times re, right? Which is 0.05 times 0.005 times re is 1494, which is almost 0.37 meters. Now, what is the thermal entrance length? Xt is 0.05 times d times red times pr, right? Just you just multiply it by Prandtl number, the above thing. So 0.37 times Prandtl number. What is the Prandtl number? 0.69. So it is 0.26 meters. So the thermal boundary layer becomes fully developed quicker than the hydraulic dynamic layer. Okay. Now, because the tube is 2 meters long, so the flow becomes fully developed at the, like, before the exit, and we have been given the specifications for the exit of the tube, right? TS at the exit, at the outlet. So now, because there is a laminar flow and the heat flux is constant, what is the Nusselt number? It is constant. It is 4.36, I think. Yes. So where did I get this value? Look at the data book. So Nusselt number is 4.36. It is constant. Now with this as the Nusselt number, how do we calculate H? H is Nu times K over dH, right? which is 4.36 times what is K, 0.0338 over DH, which is 0.005. This gives us 29.47. What is the unit? Everything is in SI, so watt per meter square Kelvin or degree Celsius. 29.47, okay. Now, once we have this H, now the problem becomes very, very simple, okay. So, uh, you can define the Q dot in two ways. I mean, Q dot, okay, how do I explain it? I mean, one is you use a Newton's cooling law in which you say Q, the heat flux is H times, this is the convective way, T is at the outlet minus T mean at the outlet, right? This is the simple, I mean, how the heat flux equation works for the convection. Now you can use the Newton's cooling law as well, which states that Q, the heat flux is m dot times Cp times T mean at the outlet minus T mean at the inlet. So this is the overall how much temperature difference happened from the inlet to the outlet. And you divide it by the perimeter, which is pi. You divide it with the surface area. So pi times d times L. So m dot Cp delta T over the area. This is Q double dash. Q double dash. This is the heat flux per unit area, right? Now we we just equate these two equations. So because both are Q double dash, so we are going to say H times TSO minus T mean at the outlet is same as m dot Cp T mean at the outlet minus T mean at the inlet over pi times D times L. So you can say, what do we want to calculate? This is what we want to calculate, right? This thing, T mean at the outlet. So for this, you will just isolate this term. So you send H below and you subtract TSO. So you will get T mean at the outlet is H times TS at the outlet plus m dot Cp over pi dl times T mean at the inlet is the first term. Let's scroll it a bit. Okay. And divided by m dot, same thing, m dot Cp over pi dl plus h. I could have, you might say that I could have just sent the h below and TSO over there, and that would have been another way. But again, you need to remember that what I'm doing here is I'm splitting these two terms, TMO separate and TMI separate, because we do not know a few terms. We directly want to use, we directly want to calculate TMO based on, first of all, splitting this into two separate terms and then sending out the terms here so that we can get TMO. Even if you use like that way, you'll get the final answer because we know all the variables, we just don't know TMO, right? So I'm going to use this form. For this, we'll have, so H is, how much is H? 29.47 times what is TS outlet? It has been given as 160 degrees Celsius, right? Plus what is m dot? M dot is 135 times 10 to the power minus 7 times 1014, I think, yes, over pi times 0.005 times what is the length? Length is 2 meters times TMI. What is the inlet temperature? 100 degrees Celsius. Now again, better use Kelvin if you are a bit doubtful. But I'm sure here, gradually with time, you'll know when to use Kelvin, when to use degree Celsius. So, but if you're unsure, always use Kelvin. um, divided by, I have probably repeated this almost 10 times, I think, but still I feel it's important. Over same thing. So 135 times 10 to the power minus 7 times 1014 over pi times 0.005 times 2 plus h is 29.47, right? From this, you're going to get Tm outlet as 152.3 degrees Celsius. This is the final answer. Okay. So this is the mean temperature at the outlet of the tube. Now, from this, what do we want to calculate? We want to calculate the heat flux, right? Q dot. So which equation to use? This equation, right? Let's use this one because we know TSO also, right? So Q is H times TSO minus TMO, which is the final value which I have is 7.16 watt. So this is the H. There's a B part to the question as well. It says, if the tube length of part A were reduced to 0.2 meters, how would the flow conditions at the tube exit be affected? Okay, so the flow is not fully developed by then. Or is it? Let me see. Yes, 0.26 is the, so even thermal boundary layer hasn't fully developed by the time the length, the water reaches 0.2 meters. So would the value of the heat transfer coefficient at the tube exit be greater than, equal to, or smaller than the heat transfer coefficient for the part A? What do you think? So usually when the thermal boundary layer hasn't fully formed, the flow is relatively turbulent. So the heat transfer rate for turbulent flow is relatively always higher. So because the flow hasn't fully developed by now, so we can say because the heat transfer rate is higher, so Nusselt number is higher. Because Nusselt number is higher, so heat transfer coefficient is also higher because other terms remain constant. So that's why we can say that the B part's answer is it will be greater than the value for part A. They are not asking us for the exact calculations because the correlations don't exist. Uh, okay, that's it, I think. So I have one more problem today. So I'm thinking which one to pick up. Okay, this is interesting. Let's take this one. At least looks interesting. Looks a bit practical as well. So you have been asked to perform a feasibility study on the design of a blood warmer to be used during the transfusion of a blood to a patient. The exchanger is to heat blood taken from the bank at 10 degrees Celsius to 37 degrees Celsius, which is the typical body temperature, at a flow rate of 200 ml per minute. Okay. The blood passes through a rectangular cross-section tube, which is 6.4 mm times 1.6 mm. 6.41. Okay. There's the tube cross-sectional area, which is 6.4 times 1.6, which is sandwiched between two plates held at a constant temperature of 40 degrees Celsius. So we know that the temperature also is constant at 40 degrees. Uh, and the surface which is exposed to the, so like, this is the surface which is being exposed to the constant temperature, not the top one. Okay. So 6.4 mm. So yeah, okay. And compute the length of the tubing required to achieve the desired outlet conditions at the specific field flow rate. Specified flow rate, assume the flow is fully developed and the blood has the same properties as water. Okay, so blood has the same property. So we have to use the water's properties. And we know that the temperature at the outlet, so T mean at the outlet is 37 degrees Celsius. T mean at the inlet is 10 degrees Celsius. The cross-sectional area AS is okay. I mean, take your 1 minute and then I'll discuss. I'll pause for a minute. Meanwhile, I just write down the properties of water. Okay. Um, Assuming T mean as 300 Kelvin, we will calculate the properties. Okay. So what properties have I got? I'm taking 300 because it is the nearest value which is available in the table which I've got. You could have used the exact the average of 10 and 37 and then converted it to Kelvin, and then that would have been the correct properties, but usually they don't vary much. So it's okay. You just find the nearest value which is available in your table, okay? So CP is 4179. Everything is in SI units. The density is 1 over VF, which is 997 kg per meter cube. Then VF is uh, mu F, VF, this is new, and this is also new, uh, is 8.58 times 10 to the power minus 7. Oh, and what else? Okay, thermal conductivity K is 0.613 watt per meter Kelvin, and Prandtl number is 5.83. Okay. For this, we are going to use the LMTD method, which is log mean temperature difference, and the NTU, our university's name, number of transfer units. Okay, so Q, can I use a different pen? I'm just bored of. I don't want red. Okay, green is okay. So you can say Q, which is the heat flux, is m dot Cp times the temperature is constant this time, right? That is why we are using the LMTD method. M outlet minus T M at inlet. This is a simple heat balance equation. Q is how much heat has come inside m dot Cp delta T. Simple, right? Now, from the LMTD point of view, what is Q? Q is the average heat transfer coefficient times the surface area times delta T LMTD, right? So these two are the ones which we are going to equate. Now, what is delta T LMTD? Delta T LMTD is defined as delta T1 minus delta T2 over ln of the same thing, delta T1 over delta T2. Now, what is delta T1? What is delta T2? Uh, okay. Um Delta T1 is the temperature difference at the first point. So the walls are being maintained at 40 degrees Celsius and the blood is at how much is the blood? I think, okay, give me a sec. degrees and what do we have? 37, 10 to 37. Okay, so delta T LMTD here would be, what is the delta T at the first point? It is 40 minus 10, right? Minus, what is the delta T at the end? The temperature of the wall still remains constant, but the internal temperature changes to 37 degrees Celsius over ln of uh, delta T1 over delta T2, which is 40 minus 10 is 30 over 40 minus 37 is 3. So this is the value which I have is 11.7 degrees Celsius. This is the delta T LMTD. Now, to calculate, we ultimately want to calculate the heat transfer coefficient, the average heat transfer coefficient. For that, we need the Reynolds number. So let's again begin. RED is U mean times DH over nu, right? We are using nu this time. So 0.326 times 0.00256 over nu, which is 8.58 times 10 to the power minus 7, which is 973. This means which flow is it? It's a it's a laminar flow, right? So okay, uh, how, like for example the DH you can again, so this is a rectangular plate, right? How did I calculate DH? DH was 4 times A over P, which is 4 times 6.4 times 1.6 over 2 times 6.4 plus 1.6 mm, which came out to be 0.00256 meters. This is how I got DH. And the area was 6.4 times 1.6, which is 1.024 times 10 to the power minus 4. This is m square, but here I'm writing it in meter square. Again, SI units. So from this, I calculated the mean velocity, um. Was m dot over rho times AC. This is AC, right? Which is, what is m dot? You can assume that it is, m dot is rho AV, right? So rho times AC times, I mean, this is how we, like, we want to get u dot, right? Wait a sec. I think I'm making a mistake. Do we know m dot? M dot is, uh, how much is it? We need the density as well, right? But we know the flow rate, which is 200 ml per minute. So we are going to say 200 ml over 60 seconds. This is the flow rate, times 10 to the power minus 6 meter cube over ml. This is the density in terms of volume over liters. So we are, right now I'm just converting ml to meter cube. How am I doing this conversion? This is simply, you can say 1 meter cube is 1000 liters. From this you can calculate, uh, you can convert this ml to meter cube. Why am I converting? Because I want to divide it finally by the area. Now what is the area? Area is 1.024 times 10 to the power minus 5 meters square. So from this you will get 0.326. If it got a bit confusing for you, just simply think in a way, how can you calculate the mass flow rate from the volume flow rate? Volume flow rate is simply 200 ml per minute. So I converted that to ml per second by dividing it by 60 seconds. Now I multiply it by 10 to the power minus 6 because I wanted to convert ml to meter cube. And the conversion rate is this, I think you must know. which is 1000 liters is 1 meter cube. From that, you will get this. And then you are dividing the complete thing by 1.024 times 10 to the power minus 5, which is the area. And then from this, you will get the final value 0.326. Now the density got cancelled. The density got cancelled because we were having mass flow rate here and we converted it to meter cube, right? So that's why we have this final value 0.326 meter per second. Okay. Um, okay. So now we are going to jump into another table, which so if we have a rectangular cross sectional area, and this is A, this is B, then based on A by B values, there is value of Nusselt number. Okay. So for this, we have A by B is 6.4 over 1.6, which is 4. So for A by B equal to 4, we are going to get Nusselt number as 4.44. You can get this value directly from the tables in the data book. Now from this, we calculate H. H is Nusselt number times K over D, right? Which is 4.44 times 0.613 over D is 0.00256. The value which I've got is 1063 watt per meter square, degree Celsius or Kelvin. This is the heat transfer coefficient for this problem. Now, once we have the heat transfer coefficient, how do we proceed? How do we proceed? We jump back to the first equation, right? Why did we calculate this h? This is h bar. Okay. Why did we calculate this? We calculated this for this equation, for this thing, right? And do we have these things? Yes, we do have these things. So I'm going to say m. So basically, area of the surface for the second part of that equation is the perimeter times the length, right? What is the perimeter of the tube, which is 2 times 6.4 plus 1.6 uh, times 10 to the power minus 3 times L, which is 1.6 times 10 to the power minus 2 L. This is the area of the surface. Now, what is m dot? M dot is rho times AC. This is AC, okay? AC times UM. What is AC? AC is the area of that thing, like area of the cross-sectional area, right? So density is 997 times 1.024 times 10 to the power minus 5 times 0.326, which is 3.328 times 10 to the power minus 3 kgs per second. So I what I did was I first of all built up the main equation, which is equating how the heat flow from the inlet to the outlet relates with the log mean temperature difference. From that, what values did I need? I needed delta T LMTD, I needed AS, I needed H. These two things we know M dot, we know CP. So that's how we are finally, what are they asking us to calculate? They're asking us to calculate L, the length, which is AS, because AS is perimeter times the length. So, okay. Now bringing in the whole equation, you can say that 3.328 times 10 to the power minus 3, which is m, times Cp, which is 4179, times the temperature difference, which is 37 minus 10, is 1063, which is the H, times AS. How much is AS? 1.6 times L times 10 to the power minus 2. And how much is the, what else have we got in that equation? I think there is one more thing, right? Delta T LMTD, which is 11.7. So 11.7. Okay. From this, we want to calculate this value L. So from this, we are going to get L value as 1.9 meters. We are going to need 1.9 meters long, such thin tube, rectangular cross-sectional area tube, which runs in the surface for 1.9 meters to be finally able to heat up the blood from 10 degrees to 37 degrees, which is the typical temperature for insertion of the blood inside the human body. Okay. I think, is there a B part to the problem? Assess your assumptions and indicate whether your analysis over or underestimates the necessary length. Okay. So when they ask us to assess, they typically want, so what were the assumptions which we took? We assumed fully developed flow at least at the end, right? Because then only these equations are going to be valid. Now, for a fully developed flow, we can simply calculate the XL, which is hydraulic, and XL, which is the thermal boundary, like the thermal point when the flow becomes thermally fully developed. So, what are the formulas for these? So, the flow was laminar, right? So, the X for the hydraulic, sorry, the XL for hydraulic is 0.05 times dH times RE, right? Which is the value which I've got here is 0.12 meters. And the XL for the thermal would be 0.12 times the Prandtl number. If you put in the values, the final answer which I've got is 0.73 meters. So the thermal boundary layer is still very, very significant because it is almost half the length. So the thermally, you can say that you are not overestimating the analysis, but at least hydraulically we are safe because it is 0.12 is all negligible in front of like 1.9 meters. But thermally, it might be a bit unstable. So we might, it is better to keep a little bit longer than 1.9 because I think the temperature itself of the human body is not specifically 37, it's 37.6 or something. So we can keep it a little bit longer, maybe like 2 meters, and then we can be safe. So we are currently underestimating the value of the length which is required for the for heating of the blood from 10 degrees to 37 degrees based on the thermal boundary layer development length, which is 0.73 meters. That's it. I think I've spent an hour already. Okay, I think that's it for today. Thank you for joining, and I'll see you next week, hopefully. I was not there last week because uh, I was not in Singapore. Never mind. See ya. Bye bye. Thank you. How do I stop?